Reduction of carbonyl compounds with hydrogen ions. In this section, we'll only talk about the reduction of acid chlorides, aldehydes, ketones, and esters.
An organic compound is said to be reduced when you add hydrogens to it. And hydrogen can be added in different ways. For example, you can add them as hydride ion and a proton. When you say hydride ion, it's going to have two electrons on it. Say, for example, when both of these electrons are going towards one hydrogen, then the remaining hydrogen is going to have a positive charge on it, right? Or you can add them as two hydrogen atoms, right, where each of the hydrogen is going to have its electron on it. Or you can add them as two electrons and two protons separately. In the case of carbonyl compounds, the hydrogens will be added in the form of hydride ion. Here are some hydride ion donors. We have sodium borohydride. This one right here is sodium borohydride. And next we have lithium aluminum hydride, which is a very powerful hydride ion donor, and therefore it's a very powerful reducing agent. And there are also milder versions of lithium aluminum hydride. One is diisobutyl aluminum hydride, which we generally call as dibol, and the other one is lithium tri-tertiary butoxy aluminum hydride, where three hydrogens from here has been replaced by the alkoxy groups. When aldehydes and ketones react with sodium borohydride, it's going to give the corresponding alcohol. In the case of an aldehyde, we'll get a primary alcohol, but in the case of a ketone, we'll get a secondary alcohol. Now, this reaction takes place in two steps. First, we needed to add sodium borohydride, and the next step, we have to add the acid. Only after the first reaction is complete, we are going to add acid to the reaction. Let's take a look into the mechanism. First, to begin with, the aldehyde or ketone is going to react with the hydride ion nucleophile. So how do we get the hydride ion nucleophile? Let's go back to a structure for sodium borohydride. So in sodium borohydride, the sodium is going to have a positive charge and the BH4 is going to have a negative charge. Let's expand the structure. So we have a positive charge on sodium and we do have a negative charge on BH4. So in BH4, this bond right here is going to be polar because there is greater electron density around this hydrogen, and because of which it's going to react as if it is a hydride ion. So this hydride ion will go and make a nucleophilic attack on this electrophilic carbon, thrust these electrons onto oxygen to give us the alkoxide ion intermediate. So this is the hydride ion that is getting added. Okay, once this alkoxide ion intermediate is formed, it's going to react with the acid in the second step. Okay, remember, we only needed to add the acid after the first reaction is over. Okay, so we need to get the alkoxide ion first, and then only we have to add the acid. Okay, so this is going to protonate this alkoxide group. To give us the alcohol that we want, which is the nucleophilic addition product. Acid chlorides can also react with hydride ion, but here in this case, since there is a leaving group, it's going to undergo two successive reactions with sodium borohydride. In the first reaction, it's going to give us the aldehyde, and that aldehyde is going to undergo another reduction with sodium borohydride to give us the alcohol. Let's take a look into the mechanism of how the acid chloride is converted into alcohol. To begin with, so you have this acid chloride. It's going to first react with the first hydride ion. The hydride ion will make a nucleophilic attack on this electrophilic carbon, thrusting these electrons onto oxygen to give this tetrahedral intermediate. Now this tetrahedral intermediate has got a leaving group. So this is weak. This is a weak base, and therefore this is ready to leave as these electrons come in, right? So this reaction right here is a nucleophilic addition elimination reaction. So it will give us aldehyde, since you know that the hydride ion is getting added to the carbonyl group. So therefore this is definitely going to produce as an aldehyde. So this is the first hydride ion that is getting added. And in the second step, it's going to react with the second sodium borohydride molecule, second equivalent of the sodium borohydride. Okay, where this is going to go attack the carbonyl-carbon thrust these electrons again, and it will result in an intermediate, but this time this intermediate doesn't have a leaving group because all of these bonds right here are strongly basic, right? So these groups right here are strongly basic and they don't want to leave. So when you add acid to this system, when you add acid to this reaction, this O minus is going to get protonated. Well, you can see that this is the first hydride ion that is added. This is going to be the second hydride ion that's added. And the nucleophilic addition product here is an alcohol, and you can see that this is a primary alcohol since this carbon where the OH is attached has got two hydrogens on it. Let's say that you wanted to stop the reduction at this stage where an acyl chloride is converted into an aldehyde. Then you can use milder versions of lithium aluminum hydride for this, because if you're going to use sodium borohydride, it's going to take all the way to alcohol. For example, when you take lithium aluminum hydride and replace the three hydrogens in lithium aluminum hydride with alkoxy groups, such as what you see in this case. This compound right here is lithium tri-tertiary butoxy aluminum hydride. Then it is going to convert the acid chloride into an aldehyde. But for this reaction, you have to make sure that the temperature is at minus 78 degrees Celsius. Like acid, chlorides, aldehydes, and ketones, esters can also undergo reduction with hydride ion. But here in this case, we cannot use sodium borohydride. Instead, we have to use a more powerful hydride ion donor, lithium aluminum hydride. Let's go back to the relative reactivity of carbonyl compounds. So we had the acid chlorides. Okay, acid chlorides are more reactive, and then we have the aldehydes, and then we had the ketones, and then comes the esters and carboxylic acids. They're going to have pretty much the same reactivity. So in the case of acid chloride and aldehydes and ketones, we were able to use sodium borohydride, right? But in the case of esters, since they are not as reactive as acid chlorides or aldehydes or ketones, we have to use a very strong hydride ion donor. So in which case we are going to use lithium aluminum hydride. Lithium aluminum hydride is a very powerful reducing agent, and when you compare lithium aluminum hydride with sodium borohydride, obviously lithium aluminum hydride is not as safe as sodium borohydride because it's going to react violently with protic solvents, and that is one of the reasons you always use dry aprotic solvents when you use lithium aluminum hydride. And also, lithium aluminum hydride is never used in places where sodium borohydride is useful. For example, in the reduction of acid, chloride, aldehydes, and ketones, we only need sodium borohydride. So in which cases, we do not use lithium aluminum hydride because it's not as safe as sodium borohydride. Now, what are the products that we'll be getting when an ester has been reduced? It's going to give us two alcohols. So here in this case, when methyl propanoate undergoes reduction, it's going to give us one propanol and methanol. So these are the products that will be obtained for this ester when it is reduced. Let's also take a look into the mechanism. Here, it's going to undergo two successive reductions. In the first step, it's going to be a nucleophilic addition elimination reaction, and the second reaction is going to be a nucleophilic addition reaction. So let's take an ester molecule and see what would be the mechanism for getting it reduced into two alcohols. So first, to begin with, we are going to have the hydride ion from the lithium aluminum hydride. Okay, attack this electrophilic carbon, thrust these electrons to form the tetrahedral intermediate. So this is our tetrahedral intermediate. This is the hydride ion that has been added. And since this tetrahedral intermediate has got a leaving group, as these electrons come in, this is going to leave. Now it has been converted into an aldehyde. Now once it has been converted into an aldehyde, it is going to react with the second hydride ion. Okay. But this time it would be a nucleophilic addition reaction. because there is no leaving group. Remember, this is the hydrogen that's been added in the first step, or the hydride ion that's added in the first step. And this one right here is the second hydrogen, or the hydride ion that is getting added. And you do have a negative charge on this oxygen, right? So with the presence of in the presence of the protic acid, this is going to get protonated to give us the alcohol. So this is the first alcohol. This is going to get eliminated as alkoxy ion, right? But in the presence of the protic acid, this is also going to get protonated, right, as methanol. So you will be having methanol and this alcohol, primary alcohol. This reaction is a nucleophilic addition elimination reaction, whereas this one right here is a nucleophilic addition reaction. Nucleophilic addition reaction. I'm just going to put it as Na. The reaction can also be stopped at the aldehyde stage by using a weak hydride ion donor. Here we'll be using dibol. Here is the structure for dibol. When this methyl butanoate is reacted with diisobutyl aluminum hydride called as dibol, then it's going to give us butanol and methanol. So here are the products that will be obtained. And the mechanism is going to be exactly the same as what we have talked earlier. And here again, we have to use a very low temperature of -78 degrees Celsius.